So what I'd like to do is take a look at some energy issues, in particular in circuits. And so basically we're going to be talking about how energy is transferred, the concept of power, and the concept of electromotive force, what we call an EMF. So let's talk a little bit about energy. Remember that we talked about how electrons or holes in semiconductors, for example, can scatter off of things, and one of the things is phonons. These are the vibrational, quantized vibrations in a solid, or impurities in the solid, or defects. The scattering process results in the slowing down of these particles. Realize in between there's an electric field that is pushing them, and that causes the gain of a kinetic energy, but then the collisions with these entities here cause them to slow down. So as a consequence, you have energy loss. Therefore, it requires a force or energy to cause current to flow through a conductor. That includes resistors, which are just poor conductors. Where is this coming from? Well, energy is provided or work is done by the source of potential difference. As we will talk about, we could use things like batteries to do that. Just a reminder that the work required to move a unit charge, this should be Q, across a potential difference V is equal to Q times V. We know that current is dq dt, and so we expect that the power expended, which is energy per unit time, for the above to be dq dt times V. Well, that's equal to IV. Realize what I'm doing here. I'm taking this quantity here, which is the work required to move the charge across the potential V, and just differentiating, and this is a constant, so you get dq dt. That's what this factor here is. But that's the current, and so you have the power expended in having current drop across a potential V is equal to I times V. So what we're talking about is the rate energy consumption. Power is defined as the energy consumed or work done per unit time. Given a quantity of material here with ends A and B, let's imagine that the two ends are at two potential, V sub A and V sub B, and there's a current I passing through this system. If we take the potential difference across this element, it would be VAB is just equal to V sub A minus V sub B. I've put them in this order because normally when current is flowing in this direction, we're talking about positive charge. So this would have a higher potential than this value, and so that's why I did it this way. So this would be a positive quantity the way I defined it. Let's take dW. dW is the work done for a differential of charge moving across this VAB. If we take the power to be dW dt, then this will be the voltage VAB, the difference of potential across this system here, times dq dt. And so that's equal to V sub A times the current. Okay, so this is a macroscopic definition of power in terms of macroscopic parameters which we can measure, the voltage and the current. If this is a resistor, then we know that we can write the current in terms of the voltage and the resistance. So I equals V over R. So substituting in for the current in terms of the voltage and the resistance, you'll get another factor of V divided by R, and so you can then replace the voltage in terms of current to give you back another form of this equation, which is I squared times R. Let me repeat that. V is related to the resistance by V equals I times R. And so if you put that in here, you'll get I squared R squared divided by R, which gives you this. Just remember that the unit of power is the watt, and a watt is 1 joule per second. The work done by the electric force on the charge carriers is converted into heat, so this is called joule heating, and it's due to all the collisions. So if you took a single particle and looked at its kinetic energy as a function of time, schematically it looks like this. The E field in the conductor causes this to accelerate, it collides and drops, it grows, collides, and so on. So you have this fluctuating motion or kinetic energy as a function of time because of these collisions. Every collision gives energy to the lattice, which is converted into heat. So kinetic energy is being converted into heat by this conduction process. There's another way of thinking about this. Consider a resistive medium with charge moving through it, and the charge has an average velocity v. We'll let it vary with position. And it's undergoing motion because of this electric field, E sub r. And for simplicity, we're going to ignore any time dependence of these two parameters. We can also write power dissipated in this conductor resistor. For that, we're going to use the charge carrier density, which remember is the density of charge that is moving under the influence of this E field. If we write down the power in terms of velocity and force, you remember that if you take force times distance, that's equal to the work done. If you want the power, you divide this by time. And so that means that if you take Fx divided by time, you're going to get this factor here, which is just the velocity. So that's the root of this equation here, where we've taken into account that these are vectors, and the components that are parallel to each other are the important ones. If we integrate this over the volume, we'll be getting the total power that is going into the entire volume of the resistor due to the fact that it has a density of charge, it has a E field, and it has a velocity. Rewriting that then in terms of the current density, we use the fact that rho times V is equal to J. And so doing that, then we have that the power is related to the integral over this dot product here. Remember, that's a scalar. Well, what is it in terms of looking at this here? It's something that's per unit volume, because we're integrating over the volume. So what it is the local rate of energy distribution per unit volume. In this case, we're talking about ohmic or joule heating. So realize this is defined at a point. So for every point inside the resistor, there's this quantity here. When we integrate over the volume, we get the total power that is expended. Here's a simple question. We have two conductors, A and B, of the same length and radius, and they're connected across the same potential difference V. I didn't show it here, but there's some sort of a source of potential connected to the ends of each of these things. The question is, the resistance of conductor A is twice that of B. So the question is, to what conductor is more power delivered? So in other words, if you have a resistance that is high here and this one's low, for the same potential you're going to get more current. So let's look at the equations. We have this relationship here that A is twice the resistance of B. Here's the power in A, V squared over R sub A. So if we put in the value of R sub A relative to R sub B, that would be 2 times R sub B. And then look at what we're left with. We have 1/2 over V squared divided by R sub B. But this quantity right here is the power that's dissipated in R sub B. So you can see here that that's 1/2 P sub B. So the result then is that the resistor B, which is the smallest resistor, has the largest power dissipated in it. And so you can think of it as being the fact that if you have the same voltage across here, you can see that if you make this smaller, you get more power dissipated. And so that's why this inequality occurs. Well, what happens when you short out a battery? You can imagine what happens. Well, we're going to look at the case where we have a battery represented by a true source of voltage and a resistance inside the battery. Now, this really is not true. This doesn't look like this. The resistance that is in fact occurring inside the battery is complex, and it has to do with the way batteries work. Nevertheless, we'll represent it like this. Okay, so here we have an open circuit and we have no current flowing. We would say that the battery is very happy. So no current, no load means that there's no resistance across here. So it's a happy battery. Now let's put across the electrodes a very high resistance. So again, we're going to end up with a small current, and we'll have a happy battery, because if you have a high resistance for a load, then you'll have small current and you still have a happy battery. Well, okay, so now let's short it out. You short this out, and the full potential occurs across these wires, at least as long as it can. and so you have a very big current because of the low resistance. In fact, the only resistance is the battery resistance. So the result is a very unhappy battery because the shorter battery has no R, big current, and so therefore an unhappy battery. Well, what this does is because the resistance in the battery is very small, the battery tries to supply the current and keep the V battery constant. So the I out of the battery is very, very large, and so the power that is being put out or dissipated inside the battery is very, very large. So what happens? The battery gets very hot. At some point, the high temperatures cause damage, and the voltage drops, the current drops, and we would say that the battery dies. In reality, you take a car battery, and suppose by accident you do this. If you can break this circuit quick enough, you won't damage the battery. You may have to recharge it, but you won't damage it. If you leave it shorted, it's a disaster. Probably remembered recently the Boeing 787 Dreamliner lithium battery problem. They were getting meltdowns just very recently. This is not really due to shorting, but bad things happened. What happened was the loads on the batteries were pretty high. They were trying to generate very high currents. So what happens in these particular batteries is it overheated. This causes what's called a thermal runaway. So in other words, as long as you keep the load on there, the temperature keeps increasing. Well, what that did was it led to cell rupture, and in some cases it led to combustion. And one of the accidents reported they actually had a fire. If you take a look at this battery and this one, the question is which one's new, which one's used is pretty obvious. This is what it looked like before it was destroyed, and this is after. The bottom line is what the battery is trying to do is at all costs to life and limb, look at this guy here, it's trying to maintain the potential across the electrodes. What is it doing? Well, that potential difference is driving the formation of an electrostatic field which drives the current around the rest of the circuit. And that's what we talked about before, having an E field inside the conductor. Well, let's look at an example. This has to do with the power delivered to a resistor from a battery. Imagine you have a battery and it has a potential epsilon. We use this notation for EMFs, but we can also use it for potential. And the battery also has an internal resistance, little r. And what we want to do is find the load, capital R, that maximizes the power delivered to capital R. This is equal to the maximum power taken from the battery. We represent the battery as an ideal EMF, which is right here, in series with the internal resistance, and then we attach to the electrodes, which are out here, so here and here, the resistor through some resistanceless wires. So that's the circuit. The equations that we want to start with is first to find the current that flows through resistance R. Well, that's simple. Here's the potential difference that's driving the whole thing. Here's two in series, so we just take the sum of those for the total resistance. So I equals V over R translates into epsilon over R plus little r. So now we find the power that's dissipated in capital R, call it P sub R, and that'll just be I squared R. So we can substitute in our current right here, which is epsilon over R plus R. We square it times R. We form that, and then to find the maximum value, we're trying to find the R, which will give us the maximum value. We differentiate with respect to R, set that derivative equal to 0, and solve for capital R. So here's the derivative that we want, and if you put in the equation for P sub R up above, this is what you get when you take the derivative. And so you get a constant divided by another constant times this set of factors up here, and that's equal to 0. Well, because these are constants, you can see that all you need to do is take the numerator and set that equal to 0. And so that's what I've done up here with a little bit more expansion. So here's the first term expanded, and then this is the combination of the second term set that equal to 0, keep working on the algebra, and so what happens is you have then equation which reduces down to the fact that r squared is equal to little r squared, and so if you want r positive, you set r equal to little r. You have the interesting situation that to get the maximum power to this resistor here, you want its value to be equal to the internal resistance. That happens a lot, and it's an example of what is called impedance matching, and it's used to get the maximum power transfer in a number of systems. This will include, by the way, alternating current systems that involve capacitance and inductance. What happens if we let R go to 0? Well, interestingly, if you look at this, P sub R will be 0, because if you come up here to P sub R, if you let R go to 0, this power goes to 0. There's a problem with that, because what it means is that you still have tons of current. So in fact is you have a maximum current that's coming out of the battery. This would be like shorting out the battery. So what about P sub R? What's happening is that you have all of the power being generated in this internal resistance. So consequently, the battery gets hot because this is where the power is being generated, and you potentially have meltdown. So that's why this is P little r here. Well, here's the plot of the P of capital R and the current I capital R. This notation is because in Mathematica it doesn't like I because it thinks it's imaginary numbers. This is the current through the resistor as a function of this resistance, and P of R is the power that's being lost or generated in that resistance as heat. So here's the equations. You just have P of R, what we determined before, the current that we determined before, and we plot them. I've just taken some simple values for little r and epsilon. So as you might expect, you have this at 0 R. This is the value of the current, which is limited by little r. So that's why we have this value here. So it drops as you increase capital R, as you might expect. This is the power that's being made into heat at the resistance R. And what you see is that it comes up to a maximum and then it decreases. And the maximum here then is the maximum power that would be transferred to the resistor. It occurs at R equals R. Notice this is a 1, and we chose little r as being 1. So you can see how it behaves, and you see how you get the maximum value in the function.